Okay, Assalamualaikum warahmatullahi wabarakatuh and very good morning. Today we will continue on our next chapter, probably on the chapter 4 if I'm not mistaken, which is on the sample preparation. Okay, so sample preparation I divided into two parts, which is on the conventional extraction and also alternative extraction, which is also known as the modern extraction method lah. Okay, so my name again is Dr. Muhammad Afiq bin Muhammad Huri. Okay, right. Without recourse to the conventional, the ultimate cannot be shown. Sumber Google je lah. Okay, so without conventional we cannot moving forward. Okay, everything kena move, kena ada something untuk permulaan lah. Okay, tapi janganlah pening kepala mana satu telur, mana satu ayam, mana keluar dulu kan. So that's it. But we need the sun is a continuous process. Okay, it's still moving forward, right? So here is the topic outline. Okay, including the theory, we will recap some of our information that we have learned in the few topics. Okay, before this, and then we will look into three extraction method. Okay, or sample preparation method. Under conventional one, which is the liquid extraction, number 2 solid extraction, and number 3 solid phase extraction. Okay, if 10 years ago, okay, solid phase extraction, okay, categorized under modern extraction method. Okay, but nowadays that there are numbers of modern extraction method, which is the moving forward of the solid phase extraction method, because of course solid phase extraction method was developed, okay, to cater the disadvantages coming from the liquid extraction, solid extraction, or solid liquid extraction. Okay, so by developing solid phase extraction, they actually successfully to counter the issues. Okay, later we will try to look at that particular thing lah. Okay, but nowadays because science is developing, try to improve, okay, improve the analytical method, improve the preparation method. So more modern methods, okay, developed, okay, to counter some of the certain issues. For instance, too much solvent use, or they want to analyze at a trace level, or they need to pre-concentrate. They don't want to use a lot amount of sample. Okay, so they tend to move towards that. Okay, so I believe you guys already learned about not I'm not sure about learn, but I think you guys already know about green chemistry. Okay, I believe you guys have heard that particular term. Alright. Okay, on theory, why we need to learn separation method? Why sample preparation is required? Kenapa kita perlukan? Okay, so most of the times, the current sample is unsuitable for analysis. Okay, so we need to prepare them. Why the current sample is not suitable for further analysis? Because sometimes the sample here is too dirty. So when the sample is too dirty, okay, it may contaminate the column, it may contaminate the analytical method, it may damage the instrument. Okay, it may give you a bad result, okay, because of all the matrix interference behind that. Okay, and then the second thing, that your sample might be too dilute. Okay, your sample might be too dilute, so you cannot detect them. Okay, especially if you want to go for the trace analysis, for example, arsenic, for example, drug analysis, okay, for example, explosive analysis. So when the sample is too dilute, you cannot determine that lah. Okay, so you need to have the sample preparation method that can pre-concentrate that particular analyte. Okay, and then sometimes present sample method is not compatible with or harmful to the chromatographic column system. For example, you would like to analyze using reverse phase HPLC. Later on we will learn about reverse phase HPLC. Okay, reverse phase HPLC, the column can be polar or non-polar. Okay, when the column is polar, okay, you cannot you cannot use, okay, the mobile phase is polar as well. Okay, so for example, okay, your column is non-polar, and then your sample is in non-polar sample matrix. Okay, so when non-polar and non-polar, if you inject into the column, it will dissolve the column. Okay, because supposedly the column should not be, the properties of the column, we should not change them. Okay, so what we can do, that the sample matrix, we extract our sample, we prepare our sample, we remove them from the matrix, so we can dissolve in another mobile phase, which is much more suitable. Okay, so I hope that clear. Alright, the next one is the application. There's a lot of application of extraction methods. Okay, micro and semi-micro analysis. Okay, usually in the extraction method, we focus on the micro or semi-micro analysis lah. Not necessarily you want to focus on the micro trace level. Sometimes you want to look at the semi-micro analysis. Okay, so and then we want to remove the impurities, as I said before this. Okay, we need to remove the impurities because we don't want them to interfere with our analysis. We don't want them to damage our instrumentation. And then the third one, because for the concentration of analytes, because we need to pre-concentrate them, or okay, because they are too concentrate, we need to dilute them. Okay, but for the dilution, I think you guys already learned that a lot, so I don't want to touch to that. So we focus on how to pre-concentrate them, how to increase the concentration, how to make them more concentrated. Okay, alright. Okay, now let's look on the focus of this particular topic lah. Okay, so in the focus of this particular topic, we will focus more on the solvent extraction method. Okay, not you, whatever involve the solvent, okay, we will focus into that. Okay, so we are not focusing into the direct injection, distillation and headspace method. So basically lah, but I need to explain basically. Okay, what is meant by direct injection. For example, you found the drug 1 gram, you just dissolve, you sedut using syringe, okay, and then you inject at the system. Okay, that's what is it. Okay, let's say for distillation, you want to separate. For example, you want to separate the alcohol from beverages. So you can do distillation, and then you take the distillate, okay, for the analysis. Okay, that's what is meant by the distillation. And then we have the headspace method. Okay, headspace method. Okay, for the headspace, I will discuss a bit lah later at the SPME. Okay, of course in the modern extraction method we have the SPME. But basically, what is the headspace method is actually you have, for example, this is particular solvent, and then you heat a little bit under here, or if it's already volatilized, you can just take the analyte, or you just suck the analyte into your syringe at this particular space lah. Okay, so that's why we call that the headspace method. Okay, right. Right, the next one, we will look into the classification of the solvent extraction method. Okay, solvent extraction method depends if the sample is solid or the sample is liquid. Okay, if let's say for example the sample is solid, you can do either batch extraction method, or you can do the continuous extraction method. Okay, so when we're dealing with this, we call as the solid extraction method. For example lah, you want to detect in sayuran lah, in vegetables, for example chlorpyrifos. So the sample is solid, what you can do that, right, so you put the cabbage that you already chopped into small pieces, you do the vortex, you add the extractant solvent, and then you extract, okay, and then you take the supernatant, and then you filter, and then you do for the analysis. Okay, that is what is one of the example lah of the solid liquid extraction method. Okay, let's say the next one is the solid liquid extraction method. I believe you guys already learned, or not already learned lah, already heard about the Sochlet extraction method. Sochlet extraction method, where the solvent is continually dripping, okay, dripping inside of this timber, if I'm not mistaken, okay, inside of this timber, and then it will drip to the distillation cup, okay, so it will continuously dripping, okay, so as the time goes on, okay, the analyte inside of this distillation cup, okay, will get concentrated, okay, so that is one of the example. And then we have the liquid extraction, okay, we can have the cross current, and then we have the counter current, okay, so it depends, okay, for example, you have only one, it depends on the system lah. If for example this the sample and then the extraction is just one way around, so we call as the cross current, okay, so for example it's actually in a reverse method, okay, so we call as the counter current. So we can have the batch and also the continuous extraction method, okay, the batch, okay, it can be the liquid extraction lah, liquid extraction, okay, or the other thing we can do the extraction is the column chromatography, but I'm not sure if I will go into that detail, okay, right, so that is the example lah, okay. Okay, now here is the equilibrium. Just a simple recap. So we already know at the dynamic equilibrium, the rate of moving forward and moving backward is occur at the same rate. Okay, so that is what means by the dynamic equilibrium. Okay. Alright, so in liquid extraction, now we look into liquid extraction. Okay, liquid extraction is the first extraction method that we'll look into in our topic today, right? So liquid extraction, also known as one of the solvent extraction lah, and also known as the partitioning lah, solvent extraction and also partitioning. Why? Because we will form two partition between two immiscible liquid, okay, at least lah two, okay. It is a method to separate compound based on their solution preferences for two different immiscible liquid, usually water and organic solvent. Okay, usually water and organic solvent. Let's say here is the aqueous. Okay, sorry. Here we have the aqueous, and here is the organic. Okay, but I need to remind you, it's not necessarily, for example, that the aqueous layer to be at the bottom or aqueous layer to be at the top. Okay, you need to look at the density of the solvent that you use. Let's say for the example, the density of the solvent is much higher compared to water, okay, so it will go to the bottom. Alright, so and the other thing I need to remind you again, it's not necessarily for the organic solvent is only the non-polar solvent, okay, it can be polar solvent such as methanol and also acetonitrile. Okay, it depends on the situation. Okay, in the KD right now, it put here is the concentration of the solution or the solute inside of the organic over concentration of the solute in the aqueous, right? But again, it's not necessarily the concentration of the solute in organic. You want to sorry, I need to reverse. Okay, it's not necessarily a waste you want to extract into the organic. Okay, so sometimes you want to extract into the aqueous layer. Okay, so it can be either. So the KD depends. Let's say if your desired phase in the organic one, so this is the formula. Let's say if your desired phase is the aqueous, right? So your raffinate is the organic layer, so it will be like this, as organic, and then we have concentration of the solute in aqueous. Okay, it depends on the desired phase. I think I already talked about this in the previous topic. Okay, so it's an extraction of substance from one liquid phase into another liquid phase. So it's extraction from, let's say for example, from this liquid phase we want to extract to another liquid phase. Alright, so let's continue. Right, here is the picture of the liquid extraction that we can do. Okay, this is not the chocolate, because it not involve any solid at all. Okay, it's involve the liquid. Okay, so okay, before that, maybe some of you can have idea in mind what is actually happen if, for example, your initial sample is solid, okay, but you want to extract them further. Okay, as long if it can dissolve totally in liquid solvent, okay, you can proceed with the liquid extraction. Let's say, for example, okay, you want to purify further, okay, so you can use liquid extraction. For example, okay, you saw that you have drug, okay, but it has also some kind of impurities, but you want to extract, okay, so we can do this. Okay, we can do liquid extraction. So in liquid extraction, we can have the continuous liquid extraction, and we can have the batch liquid extraction. Okay, this is the old one lah, old method. Okay, so it can be phase 1 or phase 2. Okay, depends on your desired phase. Okay, it's not necessarily that your desired phase above or only at the bottom. So it can be either one. So you need to know, okay, what kind of interaction, which phase that it love to, like to, we go to. Okay, so here, if you look over here for the continuous, okay, there are two kind of system. Okay, over here, okay, let's say, for example, you want to extract, okay, at the top layer. Okay, you want to extract at the top layer, so it will dripping over here over time. So here, okay, so here we heat over here, so we keep boiling, it drip here, and then it will go again here, so it continuous. Okay, that is, for example, the density of your targeted analyte is not that much, so your sample, okay, your solvent here will get concentrated over time. Okay, your sample is inside here. Okay, so for liquid extraction, that is continuous, and also, for example, you want to perform, your analyte has the bigger density than the solvent, so this the system lah. Okay, here is the system. So when you drip over here, and then your solvent, which has the higher density compared to the raffinate, okay, so we can do like this. Okay, so the process is continuous, dripping inside of this particular sample matrix or solvent, and then you drip again back to the distillation cup or distillation flask. Okay, it will get concentrated over time. Okay, so continuous can be a long time, it can be either hours, okay, it can be either days as well. Okay, alright, so we still under liquid extraction. Here is the example. You have the separating funnel, lower density liquid, higher density liquid, so you need to be careful, okay, which actually location of the analyte. Okay, so it's the funnel tab, Erlenmeyer. So here is one of the example how you can do the liquid extraction method. For example, you put the sample 50 ml, and then you add the dichloromethane, and then you shake for 2 minutes for pressure release, and then you need to you obtain the organic solution, and then you put aside. Okay, and then the aqueous solution you do repeated extraction. So as I mentioned you before, okay, for example, the first extract, okay, because for example at 1 the KD is 1, so for example you have 10, right, 10 molecule, you have 5, not 5, 10 is not a stupid example. Let's say, for example, you have 100. Okay, so if KD or KP equal to 1, okay, so when the option, so it will just 50-50 lah, 50-50, right? Let's say you have 100 molecules. Okay, so is it a good extraction method? Because you can only extract 50%. So after you have extract this one, you put it aside, so get then the raffinate. Okay, you continue for the next process. Okay, so in the next process, it will divide again into 2. So because you have left with the only 50. Okay, so you have here 25 molecules. So you can take the supernatant over here, okay, and then you put inside of your collection flux. So right now you have 50 plus 25. Is that good? That is a very good extraction method. Or you can further proceed. Okay, here you say 3 to 5 times. Okay, then the next one. Okay, so it's further divided into, let's say for example you get here about 12.5 lah, 12.5. Okay, so here you extract, then you obtain about already 50 plus 25 plus how many? 12.5. You already about 75 plus 12.5. You already get about 87.5. So 87.5% is a very good extraction method. Okay, so usually when we develop the liquid extraction method, or we want to develop any kind of extraction method, okay, the range of extraction method should be within 80 to 120%. So that's why you need to sometimes to repeatedly extract, okay, your analyte. Okay, so this is a very good example lah. So let's say over here, of course lah, the sample, okay, the amount of solvent is huge. Okay, your sample will get diluted. What you can do after that, after you collect everything, you can do evaporation of the solvent. You can reduce back to the desired volume that you really want. Right, after that you can do the analysis that you want lah. Let's say you want to focus on the liquid chromatography, or you want to go for the gas chromatography, or you just want to do the UVVs, or you want to do NMR, or you want to do the ATR, FTR. You can do that after you completed all the steps, right? Right, so here is the solvents, okay, can be used in the liquid extraction. Okay, so you need to look at the solubility in water lah. Okay, let's say your sample in water lah, or the raffinate, okay, the phase that you don't really want is water. So you need to look at here. Okay, the smaller it is, it means that it will not get dissolved in water. It is immersible in water, right? It is immersible in water. So for example, dichloromethane is immiscible. Okay, ethanol is infinity because it's totally soluble in water. Okay, so here is totally soluble in water because they have a very good attraction, okay, between them. Okay, let's say if we look at the carbon tetrachloride, okay, CCl4 CCl4 lah. Okay, so they have the non-polar properties, so they will not soluble in water. Okay, we can look at the table and we can understand. Okay, right, so let's say for example you use butanol or the ether, this is actually polar. Okay, they will soluble in water. How look at the value. Okay, based on that as well, if let's say you want to perform distillation, okay, you can try to look at this boiling point as well. Okay, let's say for example you want to do the continuous liquid extraction, you can also understand the boiling point. So let's say you want to extract using diethyl ether, so it's not necessarily for you to increase the temperature up to 100 degrees C. So it depends on the boiling point of the solvent. Okay, now we look at the specific gravity. Specific gravity is more like the density lah. Okay, the higher the specific gravity, okay, it will be at the bottom. Okay, the more heavier it is. So when it's more heavier, it will go towards the bottom. Okay, the lighter the specific gravity, the lighter the solvent, so it will be present at the above layer or at the top layer. For example, if you look over here, let's say we use hexane, okay, and then we have the ethanol. Okay, they will not merge lah because they have opposite polarity. So if you look over here, hexane, as it has lower specific gravity, it will be at the top layer lah. So here will be hexane, okay, and here will be ethanol. Okay, right. Alright, so it's not necessarily lah, okay, the LLE is only suitable for the organic compound. It can also be performed on the ions. Okay, so here is the system lah. Okay, but you need to for the ion, you need to be very careful with the pH. Okay, so certain pH might not be suitable for the extraction, certain pH okay will be suitable for that particular extraction. So if you look over here, right, so here is the organic phase, here is the aqueous phase. Okay, so you have the AQ and you have the organic phase over here. So let's say for example you want to extract, okay, these all ions. Okay, you can use the ethyl ether or isopropyl ether, but you need to make sure that the aqueous phase is 6 molar lah. You need to prepare the aqueous phase that containing 6 molar HCl. Okay, right, so that is how you can do it. So for the ethyl ether and isopropyl ether, you need to look at this particular density, okay, which where it will be located if we put in the aqueous phase. Okay, we're not really sure. Let's say for example isopropyl ether is much more lighter, it will be at the top layer lah, so you need to be very careful. Okay, right, so we have a lot over here. Okay, for toluene for silver, okay, for silver extraction, okay, so you don't need the aqueous phase to be acidic or basic. Okay, you can just use the H2O, so it kind of interesting as well. Okay, right, so it's not necessarily again only for the organic compound, you can use for the metal ion. Right, right, so here is the example that the specific, the reagent and formula. You have the extractant and then you have the extracted metal ion, and then the optimum pH value for the extraction. Let's say you want to extract aluminium 3+. Okay, you can use chloroform to extract aluminium 3+, but you need to adjust the value, the pH value of the aqueous solution 4 to 5. For example, you adjust using acid, okay, 4 to 5 value. Let's say, yeah, of course they don't mention here what kind of the aqueous. Okay, so you can use, for example, 4 to 5 is quite acidic, you can use dilute HCl, okay, for the to adjust the acidity of the aqueous layer. Okay, let's say you have this one, you want to extract Mg2+, okay, but it's basic, so you can adjust using sodium hydroxide. So you need to be creative lah. Okay, you need to be very creative. Okay, so that is the example lah. So here we look over here. Okay, we have this particular compound, okay, that is required to extract this thing. Okay, so here, okay, they are using the complexation. So reaction lah, complexation reaction. So here is the chelating agent lah, chelating agent. So you prepare this thing, and then for example you want to extract Mg2+, so you prepare hydroxyquinoline in sodium hydroxide solution, and then you extract using chloroform, this particular metal using chloroform, right? So that's how we did. Right now, okay, is the figures graph, okay, of the effect of the pH on the extraction efficiency of selected metal ion using diatazone. Okay, this is diatazone. Okay, if you look over here, diatazone, okay, they will form a complex, and then they will trap the plumbum inside here. Okay, this is the example. If for example, if you look over here, the diatazone, okay, if for example for the cadmium, okay, the optimum pH for the cadmium 2+ is at 12. But let's say for example for copper only necessarily up to pH 4 to obtain a good recovery. So for the it's not necessarily that if you are using the same chelating agent, okay, it's supposed to be at the same pH for every molecule, every ions. Okay, right, so depends. So different targeted analytes, they may have different pH. So pH is one of the variables that you can play around during the extraction process. Alright, so now let's look on the liquid extraction, how we can modify our equation. Okay, I don't really like to actually to discuss on how to derive. Okay, so usually I won't ask for the derivatives, how to derive the equation, but because we have another section. Okay, I'm afraid that if during the final exam they want to include that, so I need to explain a little bit lah. Okay, but let's say if I'm not be able to explain to you very well, okay, let's say they suggest the question to be included in the final examination, okay, I will try to oppose lah. Okay, so let's say that happen lah, I don't really know how to explain very well, so I will try to not include in the final exam. Okay, because I don't think that derivatization is necessary for you lah. It's no longer mathematics. Okay, usually we will provide you the equation at the back and then you just utilize the equation. Right, so if you look over here, KD, okay, here he put that the desired phase is the organic. Okay, so the solid concentration of solid in organic and the concentration solid of the aqueous as the raffinate. Okay, so if we want to calculate the concentration of the solute in the aqueous, okay, is the fraction solute left. Okay, multiple by total number of solute divided by the aqueous phase volume. Okay, equal to km. Okay, fraction is what? Fraction is the ratio out to 1 lah. Okay, so from 100%, okay, the ratio is we change to 0 to 1 lah. Okay, fraction of, if you have 100% over 100%, of course you get 1 lah, right? So let's say it just only about 80%, so it will be 0.8. Okay, so that's what it mean by the fraction left. Okay, let's say you have the total solute left is about 80%. Let's say total number of mole of the solute is 100 mole. Okay, so 80% of the fraction solute left in the raffinate, so you get about 80 mole. Okay, left in the raffinate. So 80 mole over the aqueous phase volume. Okay, you will get concentration lah, kan? Mole per volume is concentration. Okay, that is how you can do it. Okay, how about the solute fraction move? Okay, you need to 1 minus Q. Remember, Q is the solute fraction left in the raffinate. Okay, later I draw this first. Okay, let's say you have this particular phase. We have phases. We have phase A and phase B. Here is the organic, here is the aqueous. Okay, so the fraction left, the solute left, okay, the fraction number of the solute left in the raffinate we call as Q. Okay, so the one that actually move forward to the desired phase we call as 1 minus Q lah, because Q is the one that left at the raffinate, right? So you want that to know the fraction left over here, so you need to 1 minus Q. Let's say the Q is 80% or 0.8, so 1 minus 0.8 is 0.2 lah. So 0.2 is actually at the desired phase or the organic phase for this example lah. Okay, so if you put that particular equation inside of this equation, okay, you can have like this: 1 minus Q over M over V. Okay, then QM over V aqueous. If you want to further simplify, because here is the molecular mass, if I'm not mistaken, M, I believe is the molecular mass lah. Let's say you want to what we call, you want to change into the gram per ml or milligram. You want to in the form of mass, no longer in the form of mole. So if you want to do that, you can multiply by that lah. If not, you can just only cross the M lah, because M the molecular mass will not change, right? Okay, because we refer to the same compound. Okay, will not change. We can just simply cancel the M. Okay, so the simple equation is 1 minus Q over V organic, Q over V aqueous. Okay, because we want to make it further simplify, we don't want to have division over in the division. Okay, we can just inverse the thing. So it's become like this: 1 minus Q V AQ, and then we have divide by Q V organic. So this is how it actually gets simplified. Okay, right. So it doesn't end here. It doesn't end here. We have still further. We can still further derivatize the equation. Right. So I really hate to derivatize the equation. I'm not really good at mathematics, at what we call additional mathematics. I'm not really good at it. Right. So here Q equal to V. If for example here you adjusted them, bawa ke depan, bawa ke belakang, move it forward or move it backwards. Okay, you can sort it like this. Q equal to this lah. Okay, Q equal to this. So this is how you can calculate the fraction. Okay, let's say if you want to calculate the here is what you can calculate for the fraction of analyte in the raffinate. Let's say you want to calculate the fraction of analyte in the desired solution. Okay, for let's say in the previous example in the organic phase. So 1 minus whatever you get over here. And how to derivatize to over here, I'm not really sure lah, because it's kind of complicated. I'm not really sure. Okay, but don't worry, if let's say it's necessary for you to do the calculation, we will provide you with the equation lah. Usually we will provide you with the equation, don't worry. So if you're asking me how it gets from here to here, okay, I cannot really explain. Okay, but until here and until here I can explain lah, like just I explained before this, right? Okay, so 1 minus Q is solid fraction extracted. Okay, the next one is the percentage of the extraction. Okay, right. So percentage of extraction is equal to this one. Okay, now 1 minus Qn multiplied by 100 lah. Okay, 1 minus Qn by 100. If for example you want to use previous this one also okay lah, 1 minus Q. Okay, this is the thing. Okay, right. So N multiplied by 100. Okay, N is the number of extraction, but if only you use the equal volume of the organic solvent. Let's say you have performed the third time extraction using the same volume of the extraction solvent lah. Saya tak suka guna perkataan organic ataupun inorganic. Saya lebih suka guna perkataan extraction solvent. Okay, of course lah, usually we extract to organic solvent, but sometimes we get confused. Okay, because sometimes that the people tend to think that the organic solvent is only non-polar. Okay, what happen if for example the organic solvent is polar, and then your non-desired phase, the aqueous phase, is non-polar? For example, you not the sample is not in water, the sample is for example in the CCl4 CS2. Okay, so that's why I don't really like to use that specific term. So I love to use the EXT lah. Okay, volume of extraction. So know that specifically of the extraction. So if for example you don't want that particular phase, you can use VRAF, stand for raffinate. Raffinate is the layer that you don't really want. Okay, alright. So I don't really love to use 1, 2, okay, because it's not specific and then you tend to get confused. Okay, right. So here is how you can do. Okay, 1 minus Q multiplied by 100 lah. Okay, right, that's the thing. If for example you have multiple extraction using the same volume, then you can use N lah. Okay, right. Okay, the next question, for the liquid extraction, is it preferable us for one big batch of solvent or several smaller batch? Okay, one big batch. So let's say you have 500 ml. Okay, is it you want to extract using 500 ml? Is it okay for you to extract at one time, or you can extract, okay, for example you extract using 250 ml plus 250 ml. So we compare apple to apple lah. So 550 ml and 250 ml plus 250 ml, one time or two time, which one is better? Okay, we will look into this. Okay, let's say here is a single extraction. Okay, so 1 liter containing 10 gram of solute. Okay, so you have the organic layer 100,000 mil. Okay, then you try extract, then you recover 50. Here KD equal to 1 lah, KD equal to 1. So you got 50% recover, only 50% recover. Let's say you, where is my mouse? Oh, it goes missing. Okay, here is my mouse. Okay, so if you look over here, only 50% recovered. Okay, if you do it once. Okay, let's say for example you do it 2 times. It means that you extract with 500 mils and then you extract with 500 mils. Okay, so if we break 1 liter organic solvent into 2 equal portions, which is a 500 mil each, the first one you get 3.33 gram. Okay, if we follow that KD equal to 1. Okay, KD equal to 1, right? So you get about 3.33 gram lah. Okay, 3.33 gram. Okay, so 3.3, if you don't believe me, you can calculate again. 3.33 gram instead of 500 mil. Okay, this one you divide by 6.666 gram over 5 over 1 liter, 1000 liter. Okay, 1000 liter, 1000 ml, sorry. You will get KD equal to 1. It's KD because KD is constant, right? See. So if over here, then you take another 500. Okay, the raffinate over here you put over here. Okay, then you extract again and you get 2.222 gram. Okay, again, if you don't believe me, you can divide 2.2 over 500, 4.44 over 1000. You divide that, you still get KD equal to 1. KD should be constant, yeah. KD should be constant. Right, if you add over here, okay, 3.33 plus 2.22, okay, let's say in the collection tube or collection beaker, and then you will get the total solute extracted over here is 5.555 gram. Is that great? Yeah, that's very great. Okay, so instead of using one batch extraction method, you can use multiple batch lah. Okay, use multiple batch. Right, let's say you break up 1 liter, okay, into 4 extraction. Okay, you can get up to 4.905 gram extraction. So this recovery of 59%. Okay, so it means that multiple batch is much more better, right? Not necessarily. Okay, what I mean by batch, okay, over here say just 1000, instead of you do one time, you divide by 250. Okay, 4 times. Okay, that is what it mean by this example. Of course lah, if let's say for example you do, if you imagine 1000, okay, first you use 1000 and then the second one you use 1000 and then third one use 1000. Of course you can get a better extraction, much better than this, but we need to think that this will cause too much solvent. It will cause us, we will consume too much solvent, and then of course your analyte will be diluted, and then you need to evaporate them. You need to remove the solvent, okay, to make sure that the analyte is get at the right concentration, because we don't want it's too diluted. Okay, if it's too diluted, okay, it will make the determination difficult. Okay, so multiple extraction using same volume of extraction produce better extraction recovery. That's the conclusion lah, okay, over this particular discussion. So we are at the end of the liquid extraction, not at the end of the topic. Okay, so the liquid extraction, the advantage is simple, robust. Okay, simple is simple, robust is mean that usually we don't have the problem with the stability. It's stable. Okay, minimum operator training, it doesn't need you guys to have a specific skill, very specific skill, doesn't need that. Efficient as well, okay, and wealth of available analytical data. What is mean by wealth of available analytical data? Because liquid extraction is one of the common standard method employed in industry and any analytical method. Okay, so it's widely accepted in many standard methods, widely accepted. Okay, most of the standard methods still, okay, prefer liquid extraction over the modern extraction method. Okay, but of course they have employed, for example, SPE. Okay, that is actually we put under conventional. Okay, they actually employ the SPME. Okay, right. So this is the advantage of the liquid extraction, but of course ada kelebihan, ada kekurangan. Okay, so we have also the disadvantage of the LLE. It require large volume of high purity solvent. Okay, so it can be hazardous. Let's say you want to extract using hexane, you want to extract using benzene. Okay, so it can be hazardous. You want to extract using chloroform. Okay, it will be hazardous. Okay, yield small sample to volume solvent ratio. So yeah, sometimes look at the KD or KP. Okay, can yield a small sample to solvent volume ratio. Okay, we need to use a more large volume, but we can only extract only small amount of sample. Okay, so often form emulsion. Emulsion macam mana, nanti you guys boleh google. Dia macam kalau kata you buat extraction tu, nanti dekat sini dia akan satu layer yang macam bertepu lah, macam minyak lah, macam fatty acid punya tepu macam tu lah. Okay, lebih kurang. Okay, kalau korang pernah makan mi pama, dia ada that particular minyak yang dia bagi, that particular putih-putih tu that's yang kita kata sebagai emulsion. Okay, and it's time consuming. Okay, because sometimes you need to do multiple extraction, for example until 5 times. So kocak extract, kocak extract, lepas tu you kena pergi balik. Lepas tu kadang-kadang bila dah buat banyak kali, nak kena pre-concentrate. So when it's actually quiet time consuming. Okay, so to solve this issue, we need to have automation and also effectively to reduce the consumption of organic solvent. Okay, this is the thing where it comes to the, for example, solid phase extraction. Later on we will discuss about micro liquid extraction. Okay, later we will also discuss about the solid phase micro extraction. Okay, so a lot of other method will be discussed in the next week, if I'm not mistaken lah. Okay, right. Okay, now let's look on the solid extraction method. Okay, solid extraction method is a solid liquid extraction method. It means that our sample is solid. So inside of this timber, we put the sample. Okay, so we have the timber over here. Timber is like a porous filter lah. So kita panggil ni timber. Kita akan letak solid kita dalam ni. So our solvent akan continuously drip. Okay, continuously drip. Dan dekat collection cup ni ataupun distillation cup ni, our analyte will get concentrated. Okay, after continuous lah, dia semua akan pindah ke sini. Right. Okay, here is the apparatus lah. If you look over here, number one is the stirrer bar. Okay, yang comel hotel ni. And then we have the number 2 still pot ataupun distillation pot ataupun collection pot. Nombor 3 ni adalah distillation path. Okay, so when it is distillate, it will go through over here and will turun balik lah. Okay, and then we have the timber. Okay, timber over here, chocolate timber yang warna hijau ni. Alright, and then we have the nombor 5 ni extraction solid. Nombor 6 ni adalah siphon lah, siphon. Okay, siphon. Nanti kita akan tengok apa function siphon ni. Okay, dia sebenarnya macam bila at certain situation, bila dia overflow, dia akan automatic siphon masuk dalam ni. Ada bunyi effect lagi tu. So we have the expansion adapter untuk connect this particular arm. Okay, this particular arm to this condenser. Okay. Okay. Right, so we have the cooling water in, cooling water out. Okay, that's you supposed to know that as well, right? So here, the solid extraction, continuous extraction of component from mixture, boiling point, solvent vaporize up through the larger side of the arm. So if you look over here, here is the siphon. Okay, so when you put under heat lah, so your solvent will get evaporated and then condensed back to the inside of the timber. Laju sangat. Right, so if you look over here, when it condense, so it will increase the volume over here. Okay, until it reach certain height lah. Okay, so condense will fall into the porous cup, dissolving all desired components of a solid mixture lah. So dia akan dissolve. Okay, so bila it's continuous. Okay, when the smaller arms fills to overflowing. Okay, bila dekat ni, okay, start to overflowing. okay, dia akan initiate automatically a siphoning action. Okay, so this the interesting thing about this lah. So it's like a magic, not a magic lah, it's actually a physics science behind them. Okay, so when it's overflowing, okay, then it start to siphon. What it mean by siphon? Okay, it mean that all the solvent over here will continuously siphon into this distillation cup. Okay, so dia akan sedut masuk ke dalam ni. Okay, the solvent containing dissolved component is siphoned into the boiler below. So the process is continuous. Okay, it can take hours, it can take days. Okay, right. So residual solvent then drains out of the porous cup. So bila yang kat luar ni dah siphon, so yang dalam porous cup ni dia akan sementara nak tunggu penuh balik lah, dia akan keluar lah. So continuous process. So that is a good thing about solid extraction method. But of course lah, we have problem as well with that particular method. Right, and the cycle repeats. Okay, it should look something like this lah. Bye. See, dia sedut automatic. Bila dia dah start overflowing, dia akan lepas tu ini dia akan keluar zoom zoom zoom. Saya nak explain pun payah, so saya mampu explain pakai zoom 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 je. Okay, so yang ini nampak laju only much slower, so it can take hours. Usually we take more than hours lah, at least half a day, or it can take days, okay, for the extraction. That's why this is one of the not really popular method lah, because it takes not only use a lot of electricity and also water. Okay, so it will also take a lot of time. So disadvantage is messy, okay, time consuming, use a lot of organic solvent, it can be hazardous to health. So waste disposal problem or further concentration step, and sometimes you need further concentration step lah. So it can consume consume water and electricity. So if you look over here is example of setup at the laboratory lah. Okay, if you look over here, yang putih ni adalah timbel lah yang kita letak our sample. So here is the condenser, here is the siphon. Okay, if you look, is a continuous process. Kalau tengok sini messy tak messy, nampaklah dalam ni foto dia macam mana kan. Sometimes kalau kata not a proper ni, dia akan bersepah. Okay, can be messy as well. Okay, right, let's say you want to use the chocolate, please be careful. Usually chocolate we use for the ni lah, organic extraction method. Okay, now let's focus on the next extraction method and the conventional extraction method, which is the solid phase extraction method. Okay, here is the principle and procedure. Okay, analyze, retain on the solvent. Okay, here is the solvent lah, yang grey ni, area ni adalah solvent, while matrix interference are eluted from the cartridge. So kita gunakan cartridge ni, kita panggil binatang ni, we call this thing as the cartridge. Okay, we call this thing as cartridge, here as the solvent. So the purpose of the solid phase extraction, we want to separate our analyte of interest from other impurities or matrix interference. So the process of the solid phase extraction, we want to retain and then we want to remove the interference before we can only elute our targeted analyte. Okay, so analytes are subsequently eluted with the stronger solvent. Okay, so let's say over here, okay, you put inside of this particular solvent and then you wash your analyte. Make sure that the washing solvent of the analyte, okay, I should begin from the beginning lah. Okay, usually for the SPE, okay, there are 4 steps we call the conditioning. The first one, the second one is sample addition, the third one is washing, and the last one is elution. Right, for the conditioning, we need to put some solvent so we can activate the solvent. Okay, then we put our sample. Okay, then before that we need to really careful choosing the particular cartridge. So we need to choose the suitable solvent so it can retain our targeted analyte. And then after we add our sample, we proceed to the washing process, where in the washing process we introduce the solvent. That the solvent is not actually eluted the analyte, it just only remove the interference. Okay, so if you look over here, the solvent used for washing will be different to the solvent of elution, because solvent that we use during the washing process is the purpose only to remove the interference. So after we have already removed the interference, it comes to the final process, which is the elution process. So these are 4 steps involved in solid phase extraction. So it depends on the interaction lah. Depends on the interaction. Okay, in this case, we give the example of polarity. It can be ion exchange as well, right? Okay, there are 3 goals of solid phase extraction. Okay, the first one is purification or clean up. Okay, if you look over here, the chromatogram before the SPE clean up, okay, we have a lot of interference from the impurities. So after the SPE process, we get a better, cleaner chromatogram. So we remove all the interference. Okay, so that is one of the purpose of the separation method, and this is also the same goal for SPE lah. And then right, for the concentration, we want to concentrate our analyte. Let's say we have the sample in 1 liter, trace analysis 1 liter, but of course if it's too diluted, we are not able to determine, because it's too diluted, the sensitivity not that good, and then we need to improve that. We need to concentrate our sample. So instead of you do the vaporization process, which will take a lot of time in case of your sample is easily decomposed upon heating, so you can use SPE. So you put the 1 liter continuously over the SPE, and then it will get concentrated at the solvent, and then by elution, okay, for example, you use solvent to elute your analyte, and then you can concentrate daripada 1 liter punya analyte dalam 1 liter tu, dan you boleh elute dalam 1 ml sahaja. Okay, so this also one of the purpose of SPE. And then the third one is the solvent switch. I think earlier we already discussed to you that sometimes the matrix is not suitable for certain instrument. Okay, same goes to this particular situation. For example, we want to analyze using gas chromatography, but in gas chromatography we are trying to avoid, okay, using water as the extraction solvent, especially when you use the polar column. When you use polar column and you use water as the solvent inside of the GC, dia akan merosakkan. It will damage the coating inside of the column. It will damage the what we call the coating lah. Okay, the adsorbent inside of the column. Okay, dia akan boleh rosakkan. And of course, the H2O akan menyebabkan dia akan menyebabkan interference lah. Dia akan kacau chromatogram. Okay, so sometimes we need SPE, okay, to cater this problem. So this is the purpose. Okay, but usually SPE they focus on the purification and also the concentration. Okay, right. Right, here is the figure lah. Okay, here's the figure. Okay, poor simple preparation. Okay, we still have contaminant over here, sample from matrix. We have a lot of impurities, and then because of that we have a background interference over here. Then we want to remove the matrix interference. Okay, background interference comes from the matrix. We introduce in the solid phase extraction. So instead of this, we get very much better, cleaner chromatogram, right? So and then the other here is the other figure for the other goal of the SPE, which is the trace enrichment. For example, in the original sample, okay, in 1 liter of solution, you only get this amount of detection. Okay, but by using SPE, you pre-concentrate. You concentrated the analyte inside of the sample solution, and then you can get a better chromatogram. Okay. Okay, next one. Okay, here is the figure of solid phase extraction cartridge. So it comes from different size. Okay, so it can be 10 mil, it can be 3 mil, it can even be 1 mil if I'm not mistaken. We have a lot of size. So if you look over here at the bottom, we have the particle disc. Okay, to support lah. We don't want the absorbent ni keluar lah. So kita ada selalu kita ada benda ni. Right, so kita ada pre-filter, kita ada ring lah untuk support material. Okay, right, here is the equipment necessary for the SPE. Kalau kita tengok kat sini, kita ada pump. Okay, pump ni adalah untuk kita sedut untuk kita make sure bantu sedut ni turun lah. Okay, here is the SPE cartridge, here is the SPE chamber. Okay, and here I'm not really sure what is the purpose for this thing. Maybe dia tak nak, okay, bila dia sedut nanti dia buat 2 step. Okay, yang ni masuk sini, ni masuk sini. Dia tak nak nanti daripada sini dia contaminate this particular pump. Okay, sebab dia nanti kalau you tak buat macam ni nanti, okay, kalau kata air tu dah terlalu penuh, what is the problem with that, dia akan sedut-sedut terus masuk sini, so dia akan rosakkan pump. So you need to do 2 stages process lah. So kat sini kalau kata ada terlebih liquid pun, dia akan masuk dekat sini dulu. So dia tak akan terus masuk ke dalam pump akan rosak. So dekat sini kita ada chamber, kita letak cartridge. So dekat bawah ni lah kita akan letak collection chamber ke, ataupun kita letak waste container ke, okay, dalam ni. So the setup is like this. Okay, now let's look one by one lah the step. Okay, the first step is the conditioning and equilibration lah. Maksud kita nak sediakan solvent ni for our analyte to interact. In order proper phase interface to exist between solvent and the sample, most SPE column should be solvated prior to sample loading. A typical volume of solvent is 1 ml per 100 mg solvent. Okay, so basically, okay, at the solvent macam kita tengok tadi ada pelbagai size, dan solvent dia ada pelbagai banyak lah. So it has different weight, it's a different amount. Okay, weight pula lah, different amount. So the typical volume, you need to activate the solvent. Okay, solvated the solvent, you need to, for example, you have 1 gram. So and if for example you have 1 gram of solvent, so you need to at least solvated the solvent with 10 ml. Okay, solvent. Okay, you need to solvent and solvent. Get confused. Okay, don't get confused. So at least if let's say you have 1 gram of solvent, okay, you need to have about 10 ml of solvent. Okay. Prior to sample loading, the SPE column should be normalized to match the condition of the to ensure maximum analyte recovery. That is why it means by solvated, and also you need to activate it, okay, to match the condition of the pre-treated sample lah. For example, if the sample pH is adjusted to suppress, ensure the ionization of the analyte, equilibrate the column with buffer or salvage and ionization for weak ion exchange solvent. Use buffer to also ensure ionization solvent for maximum capacity. So contohnya kalau kata you nak buat ion exchange extraction, you want to extract ions, so you need to adjust the pH so that the solvent dia dapat form the bonding ataupun interaction, absorption with the ions. Okay, so you need to adjust that. Okay, that's why here for weak ion exchange solvent, use buffer pH to also ensure ionization of solvent for maximum capacity. Okay, so usually bila kita dapat ni kering lah kan, so you need to adjust, okay. Okay, the next process is the sample loading. Okay, sample loading extraction efficiency is flow rate dependent. So evaluation the extraction efficiency versus flow rate is a useful part of the method development process. So in the solid phase extraction, okay, it depends also on the flow rate. Not, you cannot simply think that, oh, as long you just dump over there, everything will get goes into the absorber. No, because they need still to flow. Okay, flow to waste or flow to the collecting container. So you need to have in mind, okay, if for example you put at a higher flow rate, of course they will move faster, but probability for your particular analyte doesn't have enough time to get interacted with the solvent also can occur. So you need to determine what is the optimum time. What optimum time is mean that as long you can achieve more than 80% recovery, that is good already. Okay, alright. So you need to look for that. For example, you at 1 mil per minute. Okay, 1 minute is too fast. Okay, 1 minute maybe is too fast. You only get 20%. Okay, but for example, you try at 1.01 mil per minute. Okay, so 0.1 mil per minute, and then you get about 80%, 100%, and then you don't investigate. So it will take about, let's say you have 0.1 mil per minute, so 10 mil, about you need 10 minutes, right? So but you don't investigate further. Let's say if you investigate at, for example, at 0.5, is already you can obtain about 80% recovery. So instead of you wasting 10 minutes, you can finish the process within 5 minutes. So you need to study, okay, the flow rate as well. Okay, that's the example that I can give you. Alright, so the next one is the washing off interference. Okay, so after you have conditioning, after you have loading, and then you need to wash the interference. Okay, for maximum analyte recovery, analyte retention should be maintained during this step. Okay, kat sini dimasukkan macam ni lah. Kalau kita tak nak kehilangan analyte during the washing off process, we need to maintain the pH where, or ionic strength where the analyte and adsorbent have the maximum retention. Okay, kita tak nak main tuang apa-apa solvent untuk wash the interference, kita akan remove sekali kita punya interference. Okay, that is the thing that we want to avoid. Same goes with the polarity. Kita tak nak wash guna terlalu polar solvent until we remove all of our analyte of interest. Let's say for example our analyte is polar lah. Okay, kalau kata analyte kita non polar, jangan guna solvent yang terlalu non polar. Okay, so that's make the we want to avoid the loss of targeted analyte, and also we want to remove as much as impurities as we can. Right. Then the last step of the solid phase extraction is the analyte elution, the elution process. A good elution solvent should elute the analyte is in as low of volume as possible. Okay, kalau boleh as minimum volume as we can lah. Choose a solvent mixture in which the analyte is highly soluble. Okay, it's not necessarily you need to use only 100% methanol. You can mix, for example, 50% methanol and acetonitrile. Depends, okay, what kind of variable you want to play with. Okay, elution solvents should overcome both primary and any secondary interaction by which the analyte is retained. Okay, what it means by this, okay, for example, here is the cartridge. Okay, here is the bed lah, solvent bed. Okay, we want to minimize. Let's say here is the first interaction. After we do the elution, and then suddenly it goes to here, attached to here, and then it go to here to perform the secondary interaction. So we want to reduce that particular interaction. So when we put our solvent to elute the analyte, it just go down straightly to the collection tube or collection chamber without much more interaction towards the particular solvent. Okay, so useful to elute the analyte with 2 liquids adds over 2 ml of solvent rather than a single elution step with X ml of solvent. Let's say okay, daripada instead of you use macam sekaligus lah 1 liter, okay, untuk elute the solvent, not 1 liter is too much. Instead of you use 10 ml, okay, sekaligus, okay, to elute your analyte, maybe you can use 5 ml, okay, it's better, right? Alright, type of SPE phases, packing material, selection of solvent dependent on analyte and sample matrix. Depend, kita nak pilih solvent tu yang dalam cartridge tu tadi lah, yang datang ni kan, datang lagi, so this thing, okay, we call as the solvent. So it depends on the analyte, so you need to be very careful. Okay, let's say your analyte is polar, you need to choose a polar solvent lah. Kalau analyte you non-polar, you need to choose non-polar solvent. Okay, so we have a lot of things over here. We have the CAD, CADU, CA phenyl, CnH2, blah blah blah. You need to remember. Yes, you need to remember at least one of these. Okay, usually C18 is non-polar lah, because we attach the solvent, okay, with the N alkane that have the C18 carbon lah, 18 carbon. Of course you have H as well. Okay, right. So let's say you for polar solvent, selalunya kita akan attach dengan silika lah, because silika it has this particular thing kan, ataupun kita attach dengan NH2, so dia akan ada polarity. Okay, so you need to remember one of two, just as the general knowledge. Okay, this is just general knowledge. You don't need to remember the specific names such as the SDB, SC, SWC, SAS. May get you confused, but as long you understand that, okay, for example, C18, C8, okay, or nickel or silica, it should be fine. Okay, so here is the application. Remove solvent for organic compound in aqueous environmental sample. Okay, sebab apa aqueous in water sample? Because water sample is polar, so it will not damage the solvent. Okay, same goes we dealing with the polar solvent is more suitable, okay, if you want to extract from the organic solvent or apa-apa yang more organic ataupun non polar lah, macam organic soil extract. Okay, right. Okay, here is the example where the solid phase extraction solvent cartridge is non-polar. Okay, here is silica base and then it's attached with the alkane, and alkane here is C8. Okay, and here is the particular compound you want to interact. So the non-polar area, okay, yang ni polar kan, tapi kat sini dia ada hydrophilic hydrophobic punya structure. Kat sini dia akan interact dengan ni lah. Same goes to this particular compound. Okay, yang ni sebab dia hydrophilic, so it will not interact much with this. So the hydrophobic part dia akan interact with the solvent. Okay, this is how they react. Okay, typical phases is C18 or C8 lah. Okay, so this is the specific detail, but I don't think that you need to remember that as well. Okay, unless you are dealing a lot with this, there is no problem lah, because as long you understand the concept, is better already. Right, here is the example where the solvent is polar. Okay, so we have the C here. Okay, it will interact much more towards the polar punya interaction. Okay, hydrogen bond ada. Okay, so dia ada interactive bond, dipole. Okay, so this is kind of interaction. Okay, the type of ni is adalah NH2 and also Cn. Okay, this is the famous. Don't need to remember about fluorescer, it's just a specific name. Okay, so we need to understand. Right, we of course I already mentioned about you. We have also the ion exchange SPE, specifically if we want to extract ions. Okay, kadang-kadang you tanya, oh bila you tak guna ion exchange ni untuk ion? Contohnya you nak detect arsenic, ataupun you nak detect low explosive compound, which is a lot of inorganic chemicals inside there. So you can use the ion exchange SPE in the purpose of removing interference, concentrating them. Okay, right. So here is the major interaction lah. We have the anionic and also cationic. Okay, so anion exchange. Okay, anion exchange, this is the anion exchange. Even though it's positive, why we call as anion exchange? Because it will interact with the anion analyte with a negative charge. If the solvent interacting more with the cationic charge of analyte, so we call as the cation exchange SPE. So we have the anionic exchange SPE, we have the cationic exchange SPE. So in the anionic, okay, it will interact more. We focus for separating the ionic negatively charged analyte. For cationic, we focus on the separating the positively charged analyte. Okay. Okay, here is the characteristic of solvent commonly used in the SPE. So we need to look at the polarity lah. Okay, so depends on the polarity. Okay, so non-polar towards to polar. So hexane to ST is the polar one lah. Okay, so we have the strong reverse phase or weak reverse phase. Strong reverse phase means that the more non-polar is, the more reverse phase it is. Okay, vice versa to normal phase. The more non-polar is, the more the normal phase punya characteristic. Okay, so here is the thing. Hexane, isooctane, carbon tetrachloride, bla bla, sampailah dekat methylene chloride ni diorang tak miscible, ataupun dichloromethane lah, GCM, dia tak miscible dengan air. Okay, dan ether also not really miscible. Okay, ethyl acetate is polymiscible lah. We can still separate them, but you need to have the centrifuge, okay, to help you separate them better. Okay, the other thing is actually miscible in water, so you can use this particular solvent to adjust either your analyte is polar or you can choose if you want to interact with your analyte, either your analyte is polar or your analyte is non-polar. Okay, alright, the next one is the sample characteristic to determine your SPE procedure. Okay, ni lah antara contoh chart yang kita boleh contoh, kita boleh ambil sebagai rujukan. Contohnya lah, is your sample matrix is aqueous. Let's say saya nak analyse arsenic in water. Okay, so kat sini kita determine, okay, saya nak analyse arsenic in water. Is it our sample is aqueous? Yes. Okay, so we go toward this. Okay, so is your analyte interest is more soluble in water or organics? We know that arsenic is ion, so it's actually prefer the water. So water. So is the compound charged or neutral? Okay, because charge ion. Okay, we go to charge. Okay, so here is your analyte is anion or cation. Okay, arsenic AS plus, right, dia punya charge AS2 plus, if I'm not mistaken. So it's supposedly to be cationic. Cationic. Okay, so we need to look at either is weak cation or strong cation. Okay, how to determine either is weak ion or strong cation? We look at the charge and the molecular size of the molecule. If the molecule have a huge number of charge and at the same time is the molecular size is smaller, it means that it is a strong type of ion. If for example the molecule is have lower number of charge, but at the same time the size of a molecule is huge, okay, is large, okay, so we choose the weak type of ion exchange. Okay, so this is how we choose it. Right, actually for the SPE we have we don't have lah. Actually in the market they have the automated solid phase extraction system. Okay, in our faculty we don't have this. Okay, but the best thing about it, you just put your sample container over here, they will do everything for you. Okay, alright. So solid phase extraction advantages: the extract organic phase can be injected directly to the instrument. Many established standard method using this technique. Okay, so, kebanyakannya okay, sebab SPE ni is gaining popularity in 2000s lah. So kebanyakannya standard method dah start adopting the SPE. Okay, until today. But of course lah, they try to improve the disadvantages yang kita akan tengok kat bawah nanti. So many actually established standard method that already use the SPE. Okay, so the disadvantage of the SPE, kalau contohnya terlalu banyak interference, interference tu satu hal, terlalu banyak insoluble particle, okay, particle matter, it can cause plugging of cartridge. Okay, kita boleh block sebab tu selalunya before solid phase extraction kita kena filter. Contohnya kalau you ambil pada air sungai, you kena filter dulu multiple time. Multiple time mungkin you guna sieve yang biasa, lepas tu mungkin you use the filter paper, and then baru you guna SPE. And then of course the disadvantage of the SPE, you still use large amount of organic waste, because why? You need to what we call, you need to condition, you need to wash, so you need to elute, so we still use large amount of organic solvent. That's why in the next topic, not in the next topic, in the next part we will look into the modern alternative technique, which is actually counter a lot on the large amount of organic waste lah. Kita nak kurangkan benda tu, sebab kadang-kadang organic waste ni dia membahaya kan. So the problem with the conventional extraction method, use large amount of organic solvent, alright, which can be hazardous to health. Methanol sebenarnya bahaya yang bukan kita minum lah. Yang ada dalam arak tu adalah ethanol. Never mix methanol in arak. Kalau kata macam ada kes orang mati sebab minum arak buatan sendiri, usually they actually accidentally produce methanol inside there. So kalau methanol ni sebenarnya very toxic, very toxic. I know that you guys dealing a lot with methanol. It's not what we call, it's not cancerous lah. It's not that cancerous, but if you consume, it has a very huge toxicity. Right. So the next one is the waste disposal problem, of course lah, because you dealing with the organic solvent. You need to use a lot of solvent. It will be a problem for waste disposal. Pre-concentration step needed, except for SPE lah. Let's say for the LLE and chocolate extraction, because you use a lot of solvent, so it will get diluted, and then you need to reconcentrate them. Long extraction time, LLE, not really 4 to 18 hours lah. Sometimes LLE can be done within 1 hour. Even myself also have experience at Jabatan Kimia Malaysia, so it will not take much time lah. But that is only for one extract. Let's say you need to do multiple extract, replicates, it may take about 2 hours. Right. But for chocolate, it can take hours and days. 6 hours, 12 hours, so that's, I don't really like about it, chocolate. And of course it's water and also electrical consuming, because can you imagine, you need to open the tap water for about 24 hours. You need to open the electricity for the heating purposes, for the boiling, you want to boil the solvent. And then the other problem with the particular method, especially LLE and chocolate, you need to have large amount of sample lah. Some still carry contaminants, produce interfering background. So, dia tak berapa clean sangat. Tak berapa clean sangat. So solution dia, scientists are always finding creative way to reduce hazard and waste. Iaitu yang paling sekarang ni lah, kita more towards greener. So trend has been towards using smaller quantity of hazardous organic chemical to minimize environmental impact. Misalnya apa yang kita orang buat, kita akan try cari sama ada greener solvent, ataupun we try to miniaturize, kita mengecilkan skala kepada yang lagi kecil. Alternative include solid phase extraction. Ni antara one of the alternative, but we put under we still put under conventional, because it still use a lot of solvent. Other interesting modern alternative including the SPME, liquid phase micro extraction. So that we will discuss on the next topic. Alright, that's it I think for this part. Not that topic, and next part. So this part is the end. Alright, so please watch this because it's included in the next quiz. Alright, thank you. That's it I think. Bye and selamat. Semoga cheer selalu dan sihat selalu. Assalamualaikum dan salam sejahtera.